In this video, I want to talk about how to find the eigenvalues of ordinary differential equations with Matlab. We're going to use finite difference approach and just use a standard benchmark problem to demonstrate the principles. So here's our model problem. It's a simple linear second order ordinary differential equation. Y double prime plus lambda squared y is 0. Boundary conditions are homogeneous. Y of 0 equals y1 equals 0. And this equation only has solutions for certain values of lambda. And in fact, you can demonstrate that analytically. I'm not going to go through it here, but the values of lambda for which there is a solution to the equation are integer multiples of pi, and the corresponding eigenfunctions are some magnitude times the sine of n pi x. So I want to demonstrate how to use Matlab to find these eigenvalues, or at least approximations, and then we'll compare them to these known values at the end. So to do the finite differences, we replace the second derivative term with a standard central operator. Okay, so yi represents the value of y at mesh point I. H is the mesh spacing. Okay, so we just plug in that finite difference approximation for the second derivative, put in yi for this term here, and then all we do is multiply through by h squared and collect terms of yi, and we get this. Okay, so yi minus 1 minus the quantity 2 minus lambda squared h squared yi plus 1 is 0. We can write this equation at a series of mesh points. That gives us a series of algebraic equations, and then we'll use Matlab to find the values of lambda for which a solution exists for that algebraic system and see how well those approximate the system for the differential equation. So for the sample, I'm going to choose 8 regions in my mesh. So I have boundary conditions at x equals 0 and 1. So I'm looking on the interval 0 less than x less than 1. I divide that into 8 intervals. So h now is 1 over 8. This produces 9 mesh points because I have the 2 ends plus the 7 internal points. The boundary conditions tell you the values at the ends. Those are both 0. So we're left with 7 unknowns, which is the 7 internal mesh points. If I write that algebraic equation at those 7 unknowns, then I have 7 equations, 7 unknowns, and then I can deal with the system. So here's what it looks like written as a matrix equation. So those 7 unknowns y are in this, represented by this vector y. Okay, so then I have this matrix, a tridiagonal matrix, minus 2 on the diagonal and 1's on the off diagonal. That times y plus lambda squared h squared y is 0. And this looks like the equation for the eigenvalues of a matrix. All right, so the eigenvalues of this matrix are defined by this equation as long as we call those eigenvalues e and let them be minus lambda squared h squared. So if I find the eigenvalues of the matrix, and there's 7 of them in this case, then I'll get 7 values for ei. For each of those, I can solve this equation and get 7 values for lambda, and those should represent some approximation to the eigenvalues of the differential equation. So here's code to do that. All right, so I set n equal to 7 because I'm going to have a 7 by 7 matrix. H is the mesh spacing, which is 1/8 in this case, or 1 over n plus 1. Then I have a couple of equations here set up to do the tridiagonal. So the minus 2 times I of n sets up an identity matrix with, instead of 1's, we have minus 2's on the diagonal. And then these other 2 terms put the 1's on the off diagonal, and so this gives me my matrix. Then I can find the eigenvalues of that. The Matlab function is eig. Eig of my mat gives me the eigenvalues of that. And then I sort those in a descending order, and that gives me my 7 values for the little e. Then to find lambda, I take the square root of the negative of those values. and then divide by h, and those should give me 7 values for lambda. Divide that by pi to check. Remember the analytical solution was n pi, so if I divide by pi I should get integers. All right, so then I just do some plots to check how well the numerical values give me integers, and then I look at the error in that, and we'll look at those results. So for n equals 7, if all the values are integers, then they would lie in this straight line. That's the analytical solution, and you can see that the numerical solution deviates from that quite a bit. So for the smaller values, it's quite accurate, and then it gets relatively inaccurate for the last values. All right, so the error is largest for the higher eigenvalues and best for the lower eigenvalues. So, and that's true in general for this kind of equation. So we can expect the best accuracy for the lowest eigenvalues and poor accuracy for the last ones. If I look at the error here on a log plot, this is relative error. So the difference in the eigenvalues normalized by pi divided by the analytical value, then it's less than 1% error down here for the low values, and 20% error up here at the high end. And the error monotonically increases as we go to the higher eigenvalues. If we increase the number of mesh points, we should expect more accuracy. And so this now represents a plot of 2,000 eigenvalues, the analytical ones here on the straight line, and then the numerical ones here on the blue line. And so you can see again this trend that the accuracy is best for the lower eigenvalues and not good at all for the higher eigenvalues. And we'll look at the relative error again. It's on a log plot, but you can see we get errors like 10 to the minus 7 for our smaller eigenvalues, and then it increases rapidly. It's 1% by the time you get to eigenvalues around 300, and then it's again 20% or 30% at the highest end. So we get pretty good results for the smaller values, and the more eigenvalues you need accurately, the more mesh points you're going to have to use to get that result. So that's about how this works. It's relatively straightforward. You just have to be careful setting up these matrices and then interpreting the results. If you do that properly, you should be able to have success doing this with Matlab.